Hey guys, it's Miss McCorn here. We are going to continue our Unit 5 work on kinetics, reaction rates, and introduction to the rate law. We did a little bit of work on this in class today, but we really needed to get at least one more example in before you started on the partner work. There's also another video link on Google Classroom, so you can watch the Bozeman Science link if you'd like to. That'll also clear up a little bit more for you. Speaking of Bozeman Science, I want to show you. So this is a really fantastic graphic that I found that Bozeman Science had. I am going to give everybody a copy of this when I come back on Wednesday. But we did talk about these first, second, and zero order rate here. So what that is that's that M or N in our reaction or in our rate law. So I really wanted to show you this. So when we have a zeroth order, your rate is actually equal to K. When we have a first order, your rate is K times the concentration of A or whatever your reactant is that you're looking for. And then your second order is your rate times K, which is K times your concentration squared. So I think that is really fantastic tool that we can use. Also, your overall order is, you know, M plus N. That's going to be your overall reaction order. And I think this is really helpful. So we aren't really going to do anything where we're looking for the reaction rate of the products. We're mostly going to stick with the reaction rate when it comes to the appearance, or I'm sorry, the disappearance of the reactants. So that should be really helpful when you're thinking about that. So what I'd like to do is go ahead and do a practice problem that we can do together. This is the practice problem I want to work on. So this is something similar to what we did in class. The reaction between the ground level ozone and unburned hydrocarbons from automobiles produces smog. So you see here that they have the temperature is constant here. If we change the temperature, then that would mean that we would change the entire problem. We have to keep something constant. And so for this example, the first thing we're going to do is compare rates 1 and rate 2. The reason we're doing that is because the concentration of the hydrocarbon here does not change, but the concentration of our ozone does change. So because that changes, we'll be able to first find the order of the ozone. And then the second thing we'll do is we will compare rates 3 and rate 1 here. We'll compare those two because in that one, that is where our O3 actually remains constant, but our C2H4, our hydrocarbon here, actually changes. So we'll compare those two. So we're going to find first, to find the rate law, we need to find the N and the M, and those are going to be the order of our hydrocarbon and the order of our ozone. So that's the first thing that we want to do. All right, so I wanted to get to a little blank screen so that I can work this problem out for you. So the first thing we're going to do is we are going to start with our rate 2. So we'll write our rate reaction rate 2 over rate 1. So remember, our rate reactions are K, and we're going to multiply that by the molarity of C2H4. Okay? And we're going to use first, and that has to be to the power of whatever the order is, and we're looking for that order, right? And remember, we said that the first order that we're looking for is the ozone. Okay, and we're going to do this for the reaction number 2, and we're going to multiply that by the ozone, okay? And that's going to be our N. We're actually going to be looking for, right now, we're actually looking for our N. Okay, and this is going to be, of course, for rate 2. And then we're going to divide that by K, and that, of course, is going to be the C2H4 and of rate 2, O3, and 2. So the awesome thing about this is that K is going to cancel out, right? Because K divided by K is going to be 1. And we know from the problem, when we look, if we go back, you have to rewind to do that, we know that C2H4 in rate 2, I'm very sorry, this is supposed to be rate 1, apologies. Okay, C2H4 in rate 2 and C2H4 in rate 1 are equal, so that means that divided by that is going to be canceled out. And so now what we're looking for is the N's. So in order to do that, we are going to write down our rate. So we're just going to fill in the blanks now here because we have these two from our experimental data that was given to us in the problem. So 3.00 times 10 to the negative 25th, that's a negative. And that always write your units. Remember, those units are sometimes really hard to figure out, so make sure when they're given to you that you write them. And that's divided by 1.51 times 10 to the negative 25th. And again, molarity per minute. Okay, and that is going to be equal to, and then again, we're just going to fill in what we already have. We have these here because those were given to us in the experimental data. So that is going to be 5.0 times 10 to the negative 8th divided by 2.5 times 10 to the negative 8th. Okay, and that is our N, and this is reaction 2, and this is reaction rate 1. Okay, and when we work this out easily, 3 divided by 1.5 is 2. Okay, our units cancel out. 5 divided by 2.5 is also 2 to the n power, right? Because we have to leave our n in, 2 to the n power. So what is n equal to? N must be equal to 1. So that means that O3 is a first order reaction. Okay, so we're going to clear our screen and let's go ahead and do the reaction rate for, the order for our hydrocarbon. Okay, I like green a little bit better because that red's kind of throwing me off. So rate 3, we are going to compare 3 and 1 in this reaction. And the reason we're doing 3 and 1 to find the order of the hydrocarbon was because that's where the O3 stayed constant, so we can cancel that out. So we're going to do the exact same formula, right? But it's going to be the rate 3 here for our ozone to cancel out. And then the 1 will be on the bottom because, again, we want our ozone to cancel out so we can find, that's supposed to be M, so we can look for N. Again, I get it right. Okay, so this time, because our ozone is constant here, this is going to cancel out. K is going to cancel out. And so what we're now looking for is to just fill in the blanks. So again, we already know that rate 3 is our 3.00 times 10 to the negative 25th. I'm going to skip the units just to save time. 1.51 times 10 to the negative 25th, because I don't want y'all watching this for the rest of your lives. And then I'm just going to fill these in as 1.0 times 10 to the negative 7th. Okay, and that is going to be our M over 5.0 times 10 to the negative 8th. Okay, so we're looking for our M. So again, here we have 2 is equal to, and then if you divide 1 times 10 to the negative 7th divided by 5 times 10 to the negative 8th, you've really got like almost like 1 divided by 0.5. So here we have 2 equals 2m. So m is also equal to 1, which means that C2H4 is also first order. Okay, so hopefully so far so good on this. So obviously these take a bit of time to solve. We're very, very low on time, so I'm just going to go with the overall order of this reaction. We know that the reaction order for C2H4 is 1 and for O3 is 1, so the overall order is just simply N plus M, which means that it's 1 plus 1, which the overall order of the reaction is 2. Very simple. So the last thing that it's going to ask us, let me switch screens real quick. So the last one here is to find the rate constant, K. So this is just going to fill it in and making sure that you're going to get the right units. Just using experiment 2, you can see here that you just fill in the given information for the molarity of each and then simply put in your units. All right, that's the end. I hope you guys have great, fantastic luck on the practice problems, and I will see you guys tomorrow. Don't forget to make awesome posters.